In our apparatus here, energy is transferred from kinetic energy to potential energy and potential energy to kinetic energy. So first, the instances where kinetic energy is transferred into potential energy is in these pulley systems. So when the marble goes down, it falls here, and as it's falling, it gains kinetic energy. But then as it pulls the basket down, then it raises the block up here, and that gains potential energy due to gravity. And the same with all the pulleys. This pulley system down here, and the final one where the flag is raised. In all these situations, the object is moved upwards, and if our zero reference level is the ground, then it gains potential energy.
As you can notice here, our apparatus does demonstrate a point where potential energy is converted into kinetic energy. This is most notably in the ramps, where a marble is per se to start at the top, and it has lots of potential energy. And with that potential energy, is able to gain kinetic energy as it is pulled closer and closer to the ground due to the forces of gravity.
To calculate how much gravitational potential energy we give the marble when we drop it into the apparatus up here, we first have to understand what gravity is. So gravity is the force of attraction between all objects in the universe. On Earth, it's this force of gravity that gives objects their weight. The strength of this gravitational field is measured by the acceleration of objects under that gravitational field. On Earth, this acceleration is approximately equal to 9.81 meters per second squared. Thus, you can calculate the potential energy due to gravity by multiplying this acceleration by the mass of an object and multiplying that value by the object's height. So in our apparatus, you can see that the mass of the marble is 0.05 kilograms, and the height above our zero reference level, which is the flag's height, is 1.38 meters. Therefore, using our equation here, we can multiply the mass by the acceleration due to gravity by the object's height, and we determine that the potential energy of the marble is 0.67689 joules, and due to the fact that we only have one sig fig right here, we just say 0.7 joules.
At the end of our contraption, our marble comes to a point where it pulls a flag upwards, and we're asked here to find what is the speed of how fast this flag goes upwards. So in order to do that, we first have to look at how and why does it go upwards. The answer is simple, as there's kinetic energy in the flag. So in order to do that, we must define what kinetic energy is first. So kinetic energy is the energy an object possesses while it is in motion, such as our flag rising up. And it is defined as the work needed to accelerate a body of a given mass from its rest position to its stated velocity. By gaining energy and acceleration, the object will maintain this kinetic energy until its speed changes, and we can find how much kinetic energy is in a moving object by using the equation Ke equals 1/2 mass velocity squared, and mass is m, which is equivalent to the mass the object has that is moving. So that doesn't mean we also include the mass of, the whole contraption, because that does not move while the flag is going up. And v is the velocity of the object, which is squared, representing the object's acceleration. And as I stated before, we can apply these concepts to our flag, which accelerates upward at the end of the marble run, because it possesses kinetic energy. However, in order to do that, we first have to calculate its velocity. So, velocity is distance over time, but in this case, since we haven't gone that far in physics, velocity is the same thing as speed. So, we took some measurements of how fast our marble went up. So, when the marble went down, the flag went up, and we took 10 separate measurements. We found the average to be 0.66 seconds. So, by doing that, we knew that the distance from the ground, which in this case is the zero reference level, to the flag's final position is 1.00 meters. And it does that. And by using our equation, speed equals distance over time, we find that the flag moves up at 1.52 meters per second.
So now that we know the velocity of the flag to be 1.52 meters per second, then we can use the equation for kinetic energy, as shown here, to figure out how much kinetic energy the flag has. So we take the mass of the flag, which was 0.01 kilograms, so shown here, and the velocity here, and that's squared. So we find that the kinetic energy in joules is 0.011552 joules. And again, we only have one sig fig, so we have to say 0.01 joules. And as we stated earlier, the flag starts with 0.677. The marble starts with 0.677 joules of potential energy, and the flag only ends with 0.01. And so, where did the 0.667 joules of energy go?
We lost a lot of energy in our contraction. 0.667 joules of energy, to be exact. And that 0.667 joules of energy had to go somewhere, as it can't just be lost to the empty void, as the conservation of energy says. As the energy that we put in from the top has to be the same energy that we have at the bottom, but we are allowed to lose some energy in forms of friction throughout our machine. So one of those types of friction is air resistance, which is also known as drag. Which air resistance is a type of friction caused by the resistance of opposing the relative motion of an object when it is surrounded by a fluid. In our case, that fluid is air, which is resisting the motion of our marble. And in our case, that marble, even though it is very little and minimal, it's still a loss of energy to this fluid. Next, we have rolling resistance, which is a type of friction caused by a rolling object, which is our marble, being deformed on the surface. In this case, when I'm rolling a marble on my arm, you can see it is deforming the surface that it rolls on. That's not really the case in our hard solid object here, so it ends up deforming the marble. This causes energy having to be diverted into force that helps the marble come back to its original shape, causing a loss of energy to that object. Next, we have kinetic friction, which is when two objects slide past each other, like this marble rolling down my arm. This causes their surface to rub, and energy is lost through thermodynamic properties of the objects rubbing each other. Another thing that we have in our machine is static friction, which is when an object is still and it loses energy when it starts moving. This is because when an object is still, the rough surfaces contact each other, which interlocks them, and when you try to move them, that static surfaces rub against each other and cause friction, making some energy lost to heat. And finally, we have the weight of moving objects. So, when an object is moved by the marble, such in this case, the pulley, besides just moving up the counterweight, which is what helps the next marble go into motion, you also have to lift the weight of the string, which is a bit of extra weight. And this bit of extra weight means the marble initially here needs more energy in order to lift this part, allowing the next marble to go, which also accounts as a loss of energy.
Perpetual motion machine is a device that once in motion, it will remain so until an outside force stops it. So in this case, once we place the marble on the top, it would have to remain going down and then come back to the top and go down again and continue until I were to take the marble out. So, is this possible? Let's look at the science behind this. So as stated by the first law of thermodynamics, energy cannot be created nor destroyed. It can only be changed from one form to another. Therefore, to make this apparatus into a perpetual motion machine, the marble cannot lose any energy through any of these devices going down. And as we stated earlier, when we tried putting the marble in, it lost 0.667 joules of energy through both friction and sound. And therefore, if we place the marble down and if it had to loop back up, it quickly loses energy and it would not be able to keep running. So therefore, our machine could not be a perpetual motion machine. In fact, for any machine to be a perpetual motion machine, it would have to be perfectly silent because any sound is energy lost. And it'd also have to have absolutely zero friction on all of its parts. And because on Earth, like there's air and air is a fluid, and for any movement to happen, there's always going to be a little bit of resistance moving through this air. Therefore, any perpetual motion machine will not be able to work on Earth because it will have to move through the fluid of air, and it will slow down due to air resistance.
Hey, what happened? What? Oh no! Oh no!
Oh, that's something else.
It's those tree rats, I tell you. It's the tree rats. 3.
Wait. So you ended the last video.
Messed up. Air is our fluid.
So